Hello everyone, welcome back to online lecture series on applied thermodynamics. We are continuing our topic of properties of gases and mixtures. So here in our previous lecture we continued with the van der Waals equation, and then we studied about the reduced properties and law of corresponding gases, corresponding states. So here we will have a continuation of this of law of corresponding gases. So let's copy this work into Paint. So here we are going to combine two equations. So let me write down the equations here. First is this equation. So let me write down over here that here we will be having Z is equal to PR VR upon TR into ZC. So first will be this equation, and one previous equation that we have already discussed in our previous lecture, that is PR plus 3 divided by VR square into VR minus 1 by 3 is equal to 8 by 3 TR. Okay, so these are the two equations that we have already discussed in our previous lecture, and we are going to combine these two equations. Okay, so here we are not going into the deep mathematics behind this. I will be directly writing down the outcome of combination of these two equations that we are going to accept here, that is PR plus 27 into PR square divided by 64 into TR square Z square into 8 TR Z divided by 3 PR minus 1/3 is equal to 8/3 TR. So this you can do by yourself, and still we can further modify this as Z cube minus PR divided by 8 TR minus 1 into Z square plus 27 PR divided by 64 TR square into Z minus 27 PR square divided by 512 TR square. Is equal to 0. So if you see carefully, then here the terms which are present are Z, PR and TR only. So here the Z is only the function of PR and TR. So only two things that we have written directly in this lecture is this part and this part that we need to accept. Okay, so this is the end of our previous theory, that was law of corresponding states. Now we will move forward to our new theory of today. That is Gibbs Dalton law. So here the total, we will directly go to the statement. the total pressure of gas mixture is equal to sum of partial pressure of individual component of gas mixture. So we will understand this with the help of a diagram. So here this is the arrangement that we are having. So here let's say that we are having different gases inside. First gas is over here, so here this is the gas A, which is having volume capital V, temperature, this is thermometer, red color is thermometer, this is temperature T, and pressure here is, let us say the pressure is PA. And then let's move forward to the next case here. So here we are having, let's say this is gas B, and the volume is same here. Volume is V. Here the temperature is T and pressure is PB. Now there will be a mixture of these two. So as you can see, we are having now a mixture here. So let's say that here we are having mixture A plus B, and here we are having P is equal to PA plus PB as per the Dalton's law, and the temperature is same T. Volume V. Now we will be slightly quick now. We have spent enough time on this. So as for the Gibbs-Dalton law, we can directly write down P is equal to PA plus PB. That is the first thing as per Dalton's law. And in terms of mass also we can write down this. So M is equal to MA plus MB. Okay, and suppose we need to generalize this, then we can say that P is equal to PA plus PB plus PC plus up to, let us say, Pn. So we can write down this as P is equal to sigma Pi, and then we can also write down this equation here also, that is M is equal to MA plus MB plus MC plus up to Mn, implies that M is equal to sigma Mi. Now here this here is actually a Dalton's law, and now Gibbs has modified this to give us Gibbs-Dalton law. And here the Gibbs-Dalton law is written as the internal energy enthalpy and entropy of gas mixture are respectively equal to sum of internal energies enthalpies and entropies of individual components. Of Okay, so let's write down this in mathematical form. M into U. First we will write down for an internal energy Mu is equal to Ma UA plus MB UB plus MC UC up to infinity, or we can write down Mu is equal to sigma Mi Ui. Then we have Mh is equal to Ma Ha plus Mb Hb plus Mc Hc. Then here we have Mh is equal to sigma Mi Hi, and similarly we can write down for the last term, that is entropy also, that is Ms is equal to Ma Sa plus Mb Sb plus Mc Sc plus, here we have Ms is equal to sum of Mi into Si. So let's copy this work into our main slides. and this is the Gibbs Dalton law. Now we will move forward toward next theory, that is specific heat of gas mixtures. So let's move forward with it. Specific heat of gas mixtures. So first we'll utilize this equation, that is mu is equal to sigma mi ui, and here we will modify this m into cvt is equal to sigma mi cvit, because as you all know that u can be written as cvt. We have studied this into our fundamental thermodynamics. Now T can be eliminated because the temperature will be same here, so m cv is equal to sigma mi cvi. So cv can be written as sigma mi divided by m cvi. So this is the value of cv, and now we will write down the same thing for the enthalpy part. So mh is equal to sigma mi hi, so m cpt is equal to sigma mi cpi t. So here m cp is equal to sigma mi cpi. So here cp is equal to sigma mi upon m cpi. So these are the two equations, specific heat at constant volume and specific heat at constant pressure. So let's copy this work. So this is the end of today's lecture. Thank you for watching this video.